Good evening. Abhika, can you hear me?
Yes, sir. Yes, sir. So Sonal is joining, sir.
Okay.
Sir.
So today we want to complete these two chapters. That is first one, that is hydrogen chloride and also hydrochloric acid, and the second one, that is ammonia. So without wasting time, so we can start now. That is hydrogen chloride. First of all, hydrogen chloride. In the syllabus, there is some preparative methods of hydrogen chloride. Some simple experiments shows different properties of hydrogen chloride and also the solubility of hydrogen chloride with fountain experiment and methods of preparation of hydrochloric acid. Now, as we all know, that hydrochloric acid is the aqueous solution of hydrogen chloride gas, and it's some of the reactions like reaction with ammonia and acidic properties with hydrochloric properties of hydrochloric acid, and some precipitation reactions with silver nitrate or lead nitrate solution. Now starting from this is hydrogen chloride HCl, and hydrogen chloride, here you see its molecular formula is HCl and its molecular mass is 36.5, that is hydrogen 1 plus 35.5, so around total 36.5. This is the Lewis dot structure where the hydrogen, one electron of hydrogen and chlorine each participate in covalent bonding. So chlorine having 8 electrons in its outermost shell and hydrogen having 2 electrons. So they are stable and hydrogen chloride molecule forms. Here is the electron dot structure where the only outermost shell should be represented. So one electron from chlorine and another electron from hydrogen paired up with the formation of hydrogen chloride gas. Now, the occurrence of hydrogen chloride. Hydrogen chloride gas generally occurs in volcanic emission, where the volcanic emission like this is the volcanic emission, um, the large amount of gases and some liquid materials called lava produced from here, and the gases generally contains sulfur dioxide and also some amount of hydrogen chloride gas. This is naturally occurring process, and also in our gastric juices, stomach, the production of some amount of hydrochloric acid. That hydrochloric acid is used to digest the food particles that we take. So hydrogen chloride is generally naturally present in volcanic eruption and also the gastric juice. Now we move on to the preparative methods of hydrogen chloride. Now first of all, hydrogen chloride gas is prepared by direct combination of the synthesis reaction. Synthesis reaction or combination reaction where more than one product react with the formation of a particular more than one reactant, the formation of one product. Like hydrogen and chlorine, they react with each other in presence of diffuse sunlight. Diffuse sunlight means not direct sunlight, indirect sunlight. That is the hydrogen chloride formation. This reaction is quite fast enough, and hydrogen and chlorine they react with each other with explosion, the formation of HCl. Or some important points to be noted from the preparation of hydrogen chloride. Now the important point is that moist hydrogen gas reacts with chlorine. Here moisture is required. Moisture generally acts as catalyst in this reaction, and it occurs in diffuse sunlight. Already you have mentioned that diffuse sunlight, and the reaction is explosive in direct sunlight. If you perform this experiment in direct sunlight, then the reaction will be uncontrollable. That is the explosive nature, and this reaction is negligible in the dark. No reaction, practically no reaction in the dark. And already I mentioned that moisture acts as catalyst in this reaction, so moist hydrogen gas is used. This is exceptional because moisture acts as catalyst. This type of reaction is rarely found. So in presence of catalyst, like activated charcoal reaction occurs even in the dark. If you perform the reaction in the dark, then activated charcoal can be used as catalyst. Activated charcoal absorbs hydrogen, which increases the reactivity of the reactants. Now next, move on to the preparation of hydrogen by direct combination method. This type of reaction already you have mentioned, but hydrogen, jet of hydrogen, and also in chlorine forming hydrogen chloride, jet of hydrogen and chlorine. But the mixture of hydrogen and chlorine burning by burning ribbon of magnesium, HCl is also formed, because there is so much heat is generated due to burning of magnesium, and that heat used to give energy to the reaction between hydrogen and chlorine. So no sunlight is required by this process. Now in the laboratory, we generally use such a method by which you can prepare hydrogen chloride gas on reaction with metal chlorides and concentrated sulfuric acid. The concentrated sulfuric acid and metal chloride like sodium chloride, potassium chloride, etc., it forms salt and hydrogen chloride. For example, sodium chloride, it reacts with H2SO4 with the formation of sodium bisulfate and hydrogen chloride gas. The reaction temperature is generally maintained below that of 200 degrees Celsius. If you perform this reaction above 200 degrees centigrade, what happens? We should discuss later. So sodium chloride reacts with H2SO4 with the formation of sodium bisulfate and hydrogen chloride gas at temperature below that of 200 degrees Celsius. Temperature below that of 200 degrees Celsius. This is the schematic diagram of preparation of HCl from a salt, where the round bottom flask that contains mm, uh, this round bottom flask contains the salt and the sulfuric acid. Now the hydrogen chloride gas is produced by the reaction between sodium chloride and H2SO4, and the burner is used to maintain the temperature around 200 degrees Celsius or below that of 200 degrees Celsius. And after the formation of HCl, that HCl gas is passed through this exit tube, and this is again this is passed through hydrochloric acid, concentrated hydrochloric acid, because concentrated hydrochloric acid is used, concentrated sulfuric acid, sorry, concentrated sulfuric acid is used as a dehydrating agent, because it can remove the moisture present in HCl, with the formation of dry HCl gas. So this is the laboratory method for the preparation of hydrogen chloride, where you see that the reactions may happen, that here you see that sodium chloride reacts with H2SO4 if you maintain a temperature around 200 degrees Celsius, sodium bisulfate and HCl. But if you maintain a temperature above that of 200 degrees Celsius, then the product will be sodium sulfate and HCl. Here moist HCl gas is passed through concentrated sulfuric acid, but concentrated sulfuric acid water absorbing. That's why here from you get the dry hydrogen chloride gas, and this is dry hydrogen chloride gas. So evolved hydrogen chloride gas can be dried by passing through concentrated sulfuric acid collected by the upward displacement of air, sorry, not water, air, since it is lighter than air, upward displacement of air. You can collect upward displacement of air because it is heavier than air. Here some of the informations important for this method. Which reactants are used? Sodium chloride concentration. So the product is sodium bisulfate because temperature around 200 degrees Celsius is used. That's why bisulfate is formed. Observation: the delivery to hydrogen gas is bubbled through drying agent. Here drying agent, concentrated sulfuric acid is used as drying agent and collected in the gas jar. For the purification, it is passed through concentrated sulfuric acid, which absorbs moisture. Some of the precautions should be taken. The reaction should be carried out very slowly, and lower end of the thistle funnel should be deep below the acid. Otherwise, hydrogen formed should escape through the thistle funnel. So the thistle funnel should be deep below the acid. Otherwise, what happened? The HCl gas that is formed, that also be removed from this thistle funnel. Collection: it is the heavier than air, so it is collected by the upward displacement of air. It cannot be collected over water because it is highly soluble in water. Identification: a glass rod dipped in ammonia. When it's contact ammonia, when came in contact with HCl, you get the dense white fumes of ammonium chloride. So this is the identification of HCl gas. Now this is the collection of hydrogen chloride, because hydrogen chloride is heavier than air, so it is collected by the upward displacement of air. Here is the identification of HCl. Here you see that ammonia and HCl, when comes in contact, they react with each other. Ammonia and HCl, they react with each other with the formation of ammonium chloride. The dense white fumes of ammonium chloride. So these are some important informations related to the lab preparation of HCl. Now, there are some important questions related to the lab preparation of HCl. First question is that why NaCl is preferred? Because it is cheap, less amount of cost is required. So it is cheap, it is easily available. Sodium chloride in its pure form, it is easily available. And that's why sodium chloride, you can use potassium chloride also, but potassium chloride is not so cheap and not easily available. Again, laboratory method, why concentrated sulfuric acid is used. In place of concentrated sulfuric acid, can you use other acids like nitric acid? Concentrated sulfuric acid is most non-volatile acid because its boiling point is very high. So concentrated sulfuric acid generally used, and it can displace the HCl, which is volatile, and sulfuric acid easily displaces hydrochloric acid from sodium chloride. That's why sulfuric acid is used. Nitric acid is also volatile, so nitric acid can't be preferred for this method. So nitric acid generally can't be used. It is volatile, and again it is volatile out along with HCl. So HCl gas that is formed, that is mixed with nitric acid vapors. So that's why nitric acid is generally avoided by this method. And the next important thing, that is already we have mentioned, the temperature should be kept around to 200 degrees Celsius. Now the problem is that if in this case, if you maintain a temperature around 200 degrees Celsius, then sodium bisulfate is formed in HSO4, and sodium bisulfate, if you maintain a lower temperature, then lower fuel cost, and also the sodium sulfate is non-sticky, and that's why this sodium sulfate is easily can be removed from the glass apparatus. So after the reaction is over, then you have to wash those glass apparatus that is used for the preparation of HCl. So sodium bisulfate is non-sticky, and that's why it is easy to remove from the glass apparatus. That's why the temperature maintained around 200 degrees Celsius. But if you maintain a temperature around above 200 degrees Celsius, then in that cases fuel most above 200 degrees Celsius means much fuel is required. So much fuel is wasted. First thing. Second thing, glass apparatus may crack, because if you maintain a higher temperature, then glass apparatus may crack. And the third one, that is sodium sulfate form, which is a hard crust. Sodium sulfate is hard crust, very difficult to, it is very much sticky and very difficult to remove from the glass apparatus. So washable, not so washable, and it is very difficult to remove from the glass apparatus. And that's why temperature should not be maintained above 200 degrees Celsius. In that case, sodium sulfate is formed, and sodium sulfate is very much sticky substance. And these are the important points that why we do not use the temperature above 200 degrees Celsius in the laboratory preparation of hydrogen chloride from the sodium chloride. Now, concentrated sulfuric acid. Why sulfuric acid concentrate used as drying agent? Because during the formation of HCl, it is contaminated with some amount of moisture, and that moisture, sulfuric acid is a very good drying agent, and it is unreactive towards the hydrogen chloride gas, and that's why HCl can be used, hydrochloric sulfuric acid can be used as drying for hydrogen chloride gas. Other drying agents like calcium oxide or P2O5 cannot be used as a drying agent, only because of the fact that if you use calcium oxide, this is basic, and HCl is acidic. So they react with each other with the formation of salt, and even P2O5, that is also reactive towards the HCl. And so this type of agents, they react with HCl. And calcium oxide is a basic oxide, react with HCl to form calcium chloride. And again P2O5 that react with HCl to form phosphorus oxychloride and metaphosphoric acid. These are the reaction POCl3 and HPO3. So P2O5 reacts with HCl to form phosphorus oxychloride and metaphosphoric acid. That's why P2O5 is also you can't use. And why the HCl is collected? We have already mentioned that HCl is heavier than air. HCl is 1.2 times heavy, 1.28 times heavier than that of air. The vapor density of HCl is 18.25 and vapor density of air is 14.4, and that's why HCl is collected by the upward displacement of air, because HCl is 14.4 times heavier than that of HCl. HCl also collected cannot be collected over water because HCl 1 volume of water dissolve 452 volume of HCl, so it is highly soluble in water. If you want to compare the density and solubility of the different gases, then hydrogen chloride HCl is denser than ammonia but lighter than sulfur dioxide. Again, HCl, SO2, H2S, O2, Cl2, CO2, all are heavier than air. So in all those cases, if the displacement of air is used, then upward or displacement of air should be used. Ammonia and hydrogen, those gases are lighter than air. Nitrogen almost as heavy as air. Um, Nearly they have same density. Ammonia, HCl, sulfur dioxide, they are highly soluble in water. So all those gases should not be collected by the displacement of water. H2S, Cl2, CO2 fairly soluble in water. They also cannot be collected by the displacement of water. They are partly soluble, but they are soluble. That's why they should not be collected by the displacement of water. Nitrogen, hydrogen, oxygen, they are slightly soluble, very less soluble. So these type of gases like nitrogen, hydrogen, oxygen, they can be collected by the displacement of air, displacement of water. So all those informations are important. Now we want to discuss some of the physical properties of hydrogen chloride. It is colorless, pungent, as usual short taste, but the choking odor, uncomfortable. You feel uncomfortable in the atmosphere of HCl. Already you have mentioned that it is 1.28 times heavier than that of air. That's why you collect HCl by the upward displacement of air. It is non-poisonous but causes the burning sensation. This is generally for hydrochloric acid. Fairly soluble, highly soluble, fairly means highly soluble. So HCl gas is not collected by the displacement of water, and it is liquefied at very low temperature like 10 degrees Celsius with a pressure of 40 atmospheric pressure converted into liquid, and the boiling point is minus 83 degrees Celsius and the freezing point is 113 degrees Celsius. This is the experiment by which you can prove that HCl gas is heavier than air. Now take this type of system where the upper part of the cylinder contains HCl gas and lower part it contains a candle, that is burning candle. Candle burns due to the presence of oxygen in the lower part of the cylinder. But once the another cylinder that is placed inverted way like this, then because of the fact that HCl gas is heavier, so HCl gas takes the position, takes the spaces in the lower cylinder, and the air should be removed. And when it is totally completed, the HCl gas is totally placed. In that case, the candle should be put off only because of the fact that HCl is heavier gas than air. Now another experiment is HCl gas is highly soluble in water. This experiment is known as fountain experiment, where we take a round bottom flask and that flask is filled with hydrogen chloride gas. Initially, this round bottom flask is filled with hydrogen chloride gas. Now after that, by filling hydrogen chloride gas, the mouth of the flask fixed a rubber stopper. This is rubber stopper with two holes. This is rubber stopper and it contains HCl gas, and this is two stopper, two holes, one stopper having two holes. Now through this single hole, first hole, a long jet tube. Jet tube means the very small, very thin type of tube, and that tube is placed up to the base of the flask, and another hole is fitted with a dropper filled with water. This dropper is filled with water. Now, this total system is placed inwardly. This is contains, this is no water, this is actually contains HCl gas. The upper part is contains HCl gas, and the lower part contains a blue litmus solution. After that, you use this dropper, and water should be that water is present inside the dropper should be move out of this dropper and present in the round bottom flask. Now here already some amount of hydrogen chloride, HCl, but due to the presence of water, this hydrogen chloride is dissolved in water. So here some vacuum produced, and due to this vacuum, blue litmus solution through this jet tube comes above, and through this aperture, this blue litmus solution is removed like this. After pressing the dropper, the blue litmus solution comes here, and they appears as red because this part contains HCl plus some amount of moisture, and in presence of HCl, the blue litmus converted into red one. So by this experiment, we can prove two different properties of HCl. Number one property is HCl is highly soluble in water, and number two property, that is the HCl is acidic in character. That's why the blue litmus solution is converted into red one. So this is the experiment which is known as fountain experiment, by which we prove that HCl is highly soluble in water, and also HCl is acidic character. Now some of the chemical properties of HCl. The gas is neither combustible nor supporter of combustion. It can't support the combustion, and it is unreactive towards oxygen. So it is not combustible, not burned, but it can extinguish the burning splint. Next important property, that HCl can be converted to hydrogen and chlorine by heating about 500 degrees Celsius, because HCl is highly stable compound. So lower temperature is not sufficient to convert HCl into hydrogen and chlorine. So some higher temperature is required to convert hydrogen and chlorine. Now, like all acids, not the HCl, like other acids. It reacts with the active metals like sodium, potassium, calcium, zinc, iron. They react with active metals with the formation of hydrogen gas. Here hydrogen gas, hydrogen gas, hydrogen, and the salt. With ammonia gas, this is the identification test of HCl, where the in presence of ammonia gas, it reacts with ammonia. Two gases react with the formation of solid. Two gases combine to form a solid. This is the example of that type of reaction where the ammonia gas and the HCl gas react with the formation of ammonium chloride. Now we move on to next topic, that is the hydrochloric acid. Now previously we have mentioned that hydrochloric acid is the aqueous solution of hydrogen chloride gas. So hydrochloric acid, where the hydrochloric acid after the formation of hydrochloric acid, that hydrochloric acid is passed through a empty flask. This is the empty flask, and after that it is it is soluble in water by using some inverted funnel. So actually this type of process is required for the dissolution of HCl only because of the fact that HCl is highly soluble. So some back suction is formed. So empty flask is used so that if you directly dipped into this, once HCl dissolve highly, then this part of the tube, this part of the exit tube is quite vacant, and in that case the water from this part is coming to this sulfuric acid container, and that creates the explosion, and this is known as back suction. So in order to avoid back suction, special type of funnel arrangement and also some empty flask is used so that back suction could be avoided. So here, what is back suction? Back suction, because of the fact that the HCl is highly soluble in water, the delivery tube directly immerses into water. If the delivery tube, this is the delivery tube, this is delivery tube. If delivery tube directly, this is directly immersed into water, then the rate of absorption of HCl is very high, and the partial vacuum created in the tube, in this tube, partial vacuum created, and as a result, the pressure outside being higher causes water to push down, and this result in the water passes through the delivery tube and damages the apparatus. So in order to avoid all this important back suction process, we have to use some empty flask and special type of funnel arrangement. This is the special type of funnel arrangement where the funnel is not dipped into water, but in order to avoid back suction, funnel is placed level outside the funnel. Level of funnel is some higher than that of level of water, so that the level outside the funnel falls, creating an air gap. Here some air gap is present, so the pressure and inside and outside is equalized, and as a result no water should be rising in the funnel again, or if at all rise, that should be formed. So this type of funnel arrangement should be used in order to prevent the back suction, and for this reason hydrochloric acid is not prepared by HCl gas directly into water. Now special funnel arrangement, this is the special funnel arrangement. Already you have mentioned that level of the water and outside and same outside. For this reason the gas is directly here in this picture you see that the left hand side arrangement, this is the wrong arrangement, this is the wrong arrangement, and this is the right arrangement where some air gap is present in order to avoid back suction. Okay. Now some properties of hydrochloric acid, the physical properties. The smell is pungent, that is quite similar to that of hydrogen chloride gas. Pungent, choking smell, short taste, corrosive, etc. Boiling point is 110 degrees Celsius, and already you have mentioned that hydrogen chloride is highly soluble in water, so nothing important here. The chemical properties of hydrochloric acid. The hydrochloric acid, because it is acidic character, so the litmus paper converted into red, orange, methyl orange converted to pink, and phenolphthalein is colorless in acidic medium. Uh, Metal, on reaction with metal, it forms salt and hydrogen. Salt and hydrogen. Any other cases? Salt and hydrogen, zinc chloride and hydrogen. In all those active metals, but copper is not reactive towards HCl, so no hydrogen is produced in this case. So copper plus HCl, no reaction. The action of oxides. HCl is acidic in nature, so basic oxide produced. Basic oxide reacts with HCl with the formation of salt and water, like MgCl2 plus water, like ZnCl2 plus water, like FeCl2 plus water, etc. Fe2O3, FeCl3 plus water, CuO, this is basic, and HCl, CuCl2 plus H2O. So, basic and acidic oxide. Basic oxides or hydroxide reacts with HCl to form salt and water. These are the hydroxide react similarly that of oxides, like sodium hydroxide HCl, sodium chloride plus water, calcium chloride plus water, zinc chloride plus water. The reaction of hydroxide and oxides are similar. Carbonate, in case of carbonate and bicarbonate, they produce salt, carbon dioxide and water. Like sodium carbonate produce sodium chloride, carbon dioxide and water. Calcium chloride, carbon dioxide and water. Like this. So all the carbonates and the bicarbonate produce react similarly with HCl. Sulfides, they produce salt plus sulfur dioxide plus water. Salt plus sulfur dioxide plus water. Salt plus sulfur dioxide plus water. If it is sulfides, then sulfur dioxide. If it is carbonate, then carbon dioxide. Sulfides, when it is sulfides, then only salt plus H2S. Sulfide, it produces H2S. Ferrous sulfide, ferrous chloride plus H2S. Copper sulfide, copper chloride plus H2S. Like this. Sodium thiosulfate, it produces thiosulfates, they convert sulfur, sodium chloride plus sulfur plus water. Thiosulfates converted into sulfur. Metal nitrates, generally hydrochloric acid, they do not react with nitrate, but lead nitrate, silver nitrate, mercury 2 nitrate react to give precipitate. Lead chloride, it forms PbCl2. PbCl2 forms HgCl2, forms HgCl. They form precipitate. Okay, action of metal nitrate. These are some important reactions. Here you see the reaction with oxidizing agent, very important reaction. MnO2 plus HCl, MnCl2 plus chlorine plus water. PbO2, PbCl2 plus chlorine plus water. All those reactions are important. Here also PbCl2. PbCl4 plus chlorine plus water. KMnO4 KCl plus MnCl2 plus chlorine plus water. KCl plus CrCl3 plus chlorine plus water. Bleaching powder calcium chloride plus chlorine plus water. These reactions are very important reactions of HCl. So, aqua regia. Aqua regia is the application of HCl. It is formed by 1 part of nitric acid with 3 parts of hydrochloric acid, and they can dissolve platinum, gold, etc. They are not dissolved in all other acids, but they dissolve in the mixture of 2 acids, which is known as aqua regia. So, aqua regia, nitric acid and hydrochloric acid, they react with each other with the nitrosyl chloride and nascent chlorine, and nascent chlorine, this is soluble. So in this way they are soluble in aqua regia. This is the identification test. Already we have mentioned that HCl and ammonia, they react with each other, the formation of dense white fumes of ammonium chloride. And when dilute hydrochloric acid is tested by adding some silver nitrate solution, silver nitrate, cardi white precipitate of silver chloride is formed, which is soluble in ammonium hydroxide but insoluble in dilute nitric acid. So these two important tests for the identification of hydrochloric acid. Another one, that is the manganese dioxide, MnO2. It reacts with the formation of chlorine. How will you identify chlorine? Chlorine gas, when starch, iodide, paper is held, then that paper turns blue. Starch, iodide, paper turns blue. So this is the test for hydrochloric acid. Now, some uses of hydrochloric acid, like it is used for the chlorine preparation or the ammonium chloride in dry cells, drugs, glucose from the starch. These are the some industrial uses, and also some pickling agent, used as pickling agent. And the steel should be plated with before the plating of steel with other metals, it should be purified by HCl. So this is all about hydrochloric acid. Uh, important parts of hydrochloric acid, most part of the hydrochloric acid we discussed. Now we move on to the next one, that is the ammonia. Okay, now the ammonia. By the laboratory methods of preparation of ammonia, Ammonia from different types of nitrites like aluminum nitrite or magnesium nitrite. Ammonia from ammonium salts. Ammonia by Haber's process, this is most important. Density and solubility similar like hydrogen chloride. Already we have discussed this type of experiment, fountain experiment, can also be carried in case of ammonia. Catalytic oxidation reactions of ammonia, the aqueous solution ammonia, some of the uses of ammonia. Now, here you see that the structure of ammonia, this is a pyramidal shape where the nitrogen is attached to it 3 hydrogen atoms and 1 lone pair of electron. This is lone pair. Nitrogen contains 5 electrons in its outermost shell, but out of these five electrons, only 3 electrons participate in bonding. Another 2 is present as the lone pair. Molecular formula is NH3. This is 17 because nitrogen 14 and hydrogen 1 into 3, that is 3, equals to 17. And the bond nature is covalent, but you can say that polar covalent. So this is the general information related to ammonia. General information. After that, the Lewis dot structure. Lewis dot structure means here the covalent bond is formed. 1 electron from nitrogen and 1 electron from hydrogen. They participate in bond formation, and where you see that ammonia is formed due to the where these 2 electrons are present as lone pair, and these electrons are known as bond pair. So 3 bond pair, 1 lone pair is present. Occurrence of ammonia, generally ammonia free state, in free state present in air and traces of natural water, but though they are very small amount, generally they are not present in free state. Generally they are present in combined state like ammonium sulfate or ammonium chloride or ammoniacal liquor. In this form they are present. Ammonia and ammonium salt, they are highly soluble in water, and that's why they do not present in minerals, because in minerals ammonium salts should not be present, because ammonium salts are highly soluble. Because of the fact that they are highly soluble, so they do not occur in the minerals. The pungent smell which encounters near a decay heap of organic matter or a toilet is due to the ammonia. In nearby of public toilets, you see that there is a smell of ammonia only because of the fact that the urine contains some amount of urea, and that urea is converted into ammonia by urease enzyme which is present in the atmosphere. So in near the toilet you get the smell of ammonia because of the conversion of urea into ammonia gas. Ammonia is produced due to the bacterial decomposition of urea present in urine. That bacteria is known as urease bacteria. So this is urea, and urease is converted into ammonium hydroxide, that is the ammonia, smell of ammonia is occur. Different forms of ammonia. Ammonia is commonly present in different forms like gaseous ammonia, ammonia gas, liquid ammonia, when ammonia is liquefied, it is liquid ammonia. Liquor ammonia, it is the 35% solution of ammonia, and the laboratory bench reagent, that is the 4% of ammonia solution. So ammonia present in different forms: ammonia gas, liquefied ammonia, ammonia 40s, that is the 35% urea, liquor ammonia, which is known as liquor ammonia, and laboratory bench reagent, that is generally 4% ammonia. Here ammonia solution, gaseous ammonia, ammonia, liquid ammonia, it is the liquefied ammonia obtained in cylinders. liquid ammonia, 40 saturated solution of ammonia in water, and laboratory bench reagent dilute solution of liquor ammonia. Liquor ammonia is the saturated solution, that is near about 35% ammonia is present. Now the preparation of ammonia gas, how you should prepare ammonia gas, the general methods of preparation. So ammonia gas prepared by using ammonium salt. The ammonium salt reacts with caustic alkali. Caustic alkali means sodium hydroxide or calcium hydroxide or potassium hydroxide or slake lime, caustic soda, caustic potash, etc. Slake lime means calcium hydroxide, caustic soda means sodium hydroxide, caustic potash. These are the important alkali that can be used to convert ammonium salts into ammonia. Okay, this is the ammonium salt NH4Cl reacts with calcium hydroxide. Some amount of heating is required with the formation of ammonia, calcium chloride and water. So this is the general method of the preparation of ammonia gas. You can use ammonium sulfate in place of ammonium chloride, or you can use sodium hydroxide or potassium hydroxide in place of slake lime. But the general method is always similar. That is, you have to take ammonium salt with some caustic alkali. In the laboratory, we take ammonium chloride. Generally ammonium chloride and calcium hydroxide in 2:3 weight ratio, because ammonium chloride is generally easily available and calcium hydroxide too. Now by heating, you get the ammonia gas, but that ammonia gas is passed through quicklime, calcium oxide, because moisture present in ammonia that should be absorbed by quicklime. And after that, pure dry ammonia is collected by the downward displacement of air, because ammonia is lighter than air. So ammonium chloride reacts with calcium hydroxide with the formation of ammonia, and that ammonia is passed through calcium oxide. Here it is quicklime, that is calcium oxide, quicklime, and after that you have to collect ammonia gas by the downward displacement of air. Some other ammonium salt can also be used, like sodium ammonium sulfate or calcium sodium hydroxide or ammonium chloride can be used. In all those cases, reactions are quite similar: salt, water, and ammonia. Like salt, water, ammonia, calcium sulfate, water, ammonia, sodium chloride, water, ammonia. In all those cases, the reaction is now above reactions. It can be used to identify the ammonium salt, because ammonium salts, when heated with alkali, they produce ammonia. So the smell of ammonia, from the smell of ammonia, you can identify the ammonium salts. This is the process of preparation of ammonia in the laboratory. So this is the lab preparation of ammonia, where ammonia form is collected by the downward displacement of air, and once red litmus paper is held in the gas jar of ammonia, it is converted into blue by which you can identify the ammonia gas or the nature of the gas. Here you see that drying of ammonia gas. So ammonia gas can be dried. Ammonia gas can be dried by passing through calcium oxide, because calcium oxide is basic and ammonia is also basic. So there is no reaction between ammonia and calcium oxide. That's why calcium oxide is used. So quicklime is used as the drying agent for ammonia gas. Collection of ammonia gas is collected by the downward displacement of air. Already you have mentioned that it is lighter than air. Paper density is 8.5, air, that of air is 14.4, and it can't be collected by the displacement of water also, because it is extremely highly soluble in water. 1 volume of water, it dissolves a 702 volume at 20 degrees Celsius and 1 atmospheric pressure. So ammonia can be collected by the downward displacement of air only. Some of the precautions should be taken. Number one, reactants are taken to be highly powdered form, because if you take the large particles, then the outer surface is reacted. The inner part of the chemical should not be reacted. But if you take the dust or powder form of any chemical, then each and every particle, they can participate in reaction. So that's why it is important to increase the surface area when you convert these large particles into dust one, that its surface area increases. Slack line is used in the higher ratio because may counteract with the loss of sublimation of ammonium chloride. When ammonium chloride is heated with calcium hydroxide, then some of the calcium oxide is vaporized along with ammonium chloride in order to maintain that the ratio. So the calcium hydroxide would be taken in a greater amount. Bottom flask, round bottom flask is kept in the inclined position, and ammonium nitrate is explosive. That's why it is not used. It is explosive. Any ammonium salt you can use, but not ammonium nitrate. Identification. Already you have mentioned that concentrated HCl reacts with ammonia with the formation of ammonium chloride, dense white fumes. This is the identification of ammonia gas and also for HCl gas. In both the cases, this identification test can be used. Why calcium hydroxide is generally used? Calcium hydroxide is cheaper than sodium hydroxide, potassium hydroxide, and not deliquescent. It is important. Deliquescent means it absorbs moisture and forms solution, but generally sodium hydroxide, potassium hydroxide, they are deliquescent in nature, and that's why those type of alkali should not be used in the lab preparation. Ammonium nitrate, already we mentioned that ammonium nitrate is not used because it is explosive and decomposes to form nitrous oxide and water. That's why ammonium sulfate, ammonium chloride you can use, but not ammonium nitrate. or nitrate. Round bottom flask, that should be kept in inclined position, because the reaction, in this reaction, water vapor is formed, and water vapor can, uh, like something like back suction, water vapor may again back to the round bottom flask, and that creates a problem, cracking of glass apparatus, etc. And that's why that should be present in inclined position, so that the water vapor should not be directly entering into the round bottom flask. Why calcium oxide is used as dyeing agent? Because calcium oxide is cheap, and the most important fact is that calcium oxide is basic and the ammonia is basic. Both are basic, and that's why they do not react with each other, and that's why we use calcium oxide as a drying agent of ammonia gas. H2SO4, P2O5, CaCl2, all those compounds, they are good drying agent, but they cannot be used in drying ammonia gas, because they chemically react with ammonia. H2SO4 is acidic. It reacts with ammonia with the formation of ammonium sulfate. P2O5 is also reactive towards ammonia with the formation of ammonium phosphate. And the calcium chloride, that forms addition compound. CaCl2 8NH3. So all those drying agents should not be used for drying ammonia gas. We have to remember all the balanced equations written over here. Why P2O5 is not used? Why H2SO4 is not used? Why calcium chloride is not used? In that case, you have to write those reactions with balanced equations. Metal nitride, some of the metal, though these reactions are not laboratory methods of preparation, but some metal nitrides, they react with warm water to form ammonia gas. Like nitrides, like magnesium nitride, magnesium reacts with nitrogen to form magnesium nitride, calcium, or aluminium. These nitrides, when react with warm water, they form ammonia gas. Okay. So metal nitrides can be used to prepare. Here you see magnesium nitride, magnesium hydroxide ammonia, aluminum nitride, aluminum hydroxide ammonia. Ammonia gas is liberated, and ammonium hydroxide remains in the flask, and liberated ammonia gas escapes through the delivery tube. In case of metal nitrides, drying agent, you can use calcium oxide. Collection by the downward displacement of air. Identification, which is similar to that, is ammonia plus HCl, ammonium chloride. All these are same as before. Always the lower end of the threshold funnel should be deep below that of warm water in the flask. This method is expensive because metal nitrides are costly. Magnesium metal, aluminum metal, their nitrides are very costly in nature. Now, another important method of preparation is the Haber's process. This Haber's process, uh, it is the industrial method for the preparation of ammonia. Step 1, where the nitrogen and hydrogen, they mixed in 1:3 ratio, and through pump they react in the catalyst chamber. So initial step 1, nitrogen and hydrogen they mixed is 1:3 ratio. Then after that, step 2, they passed this mixture of the gas passed over iron filings. Iron is used as catalyst, and the temperature near about 450 to 500 degrees Celsius, nitrogen reacts with hydrogen to produce methane, where the pressure is also around 200 to 500, near about it can be increased up to 900 atmosphere also. So in the step 2, they react with each other with the formation of ammonia. Now in the step 3, that ammonia gas is cooled down, and the ammonia is condensed to form a liquid ammonia. And in step 4, the unreacted nitrogen and hydrogen again pumped to back them into the catalyst chamber, where they again react with each other. So these are the steps for the preparation of ammonia from nitrogen and hydrogen. Here you see all the steps written in a single slide, where the nitrogen and hydrogen mix to 1:3 ratio, and after that iron catalyst is used, and the temperature and pressure should be maintained, and after that gas is passed cooled, and the liquid gas is collected. Liquid ammonia is collected. Now some of the important um, aspect of this process are why the conditions maintained like this, temperature around 500 degrees Celsius or the pressure around 200 to 500 degrees Celsius. This reaction is reversible and also exothermic. So in order to execute a particular reaction, if it is exothermic, then the lower temperature is required to execute the reaction in the forward direction. But here we use the temperature around 200 to 500 degrees Celsius only because of the fact that at very low temperature, the rate of the reaction is very slow. And that's why in order to increase the rate of the reaction, we maintain a temperature around 500 degrees Celsius. This is one of the important aspect of this reaction, because uh, each and every exothermic reaction, in order to execute that reaction, you have to maintain temperature that is lower temperature, but in the lower temperature the rate of the reaction should be very less. And also here we use catalyst in order to increase that temperature, increase that increase that condition rate. Now the condition here also another one, that is the uh, promoter is used here, another important, that is the promoter means which can increase the activity of catalyst. This is called promoter. Catalyst ferric oxide can also be used with promoter 2% potassium oxide and 3% aluminum oxide, which can increase the activity of catalyst. Because this reaction is reversible means the reverse reaction is occur, and proceed with the decrease in volume. So the pressure, high pressure, here the here nitrogen and 3 hydrogen reacts to form to ammonia. So here 4 moles and here 2 moles. So pressure decreases, 4 moles converted into 2 moles, pressure decreases. If with the increase in pressure, a forward reaction, more and more forward reaction will be happen. That's why pressure around 900 atmosphere, here you see that 900 atmosphere is pressure maintained for this process. So there are some of the important conditions mentioned here, and the conditions, all the conditions separately written in this case. And you see that why a higher ratio of hydrogen is taken, only because I had that 1 mole of nitrogen here in the reaction, nitrogen plus 3 hydrogen equals to 2 ammonia. So 1 mole of nitrogen reacts with 3 moles of hydrogen, and that's why higher amount of hydrogen is needed. increase in concentration favors the forward reaction. That's why higher amount of hydrogen is required for this process. Reactants always taken in the pure form, unless and otherwise the catalyst should not be work easily, because in presence of dust particles or other type of impurities, catalysts do not work. And that's why all the initial material should be taken in pure and dry. And also the optimum temperature around 400 to 500 degrees Celsius is required, because already I have mentioned that if you lower the temperature, then the rate of the reaction uh, will be very slow. Now here it is written clearly that for exothermic reaction, generally reaction favored by low temperature. But at low temperature, the speed of the reaction is very slow. At low temperature, yield of the ammonia is very low. That's why optimum temperature. Optimum temperature means not too high, not too low. Such a temperature where the ammonia production will be satisfactory. So that's why this type of temperature is used. In ammonia preparation by Haber's process, uh, no external heating is required, because this reaction is exothermic reaction. So the temperature evolved from the reaction should maintain the reaction temperature, and that's why you can't maintain the heating throughout the process, because reaction itself exothermic process and reaction gives some heating process. Pressure, already we have mentioned that 4 volume of reactant react to form 2 volumes of the product. So decrease in volume means increase in favored in increase in pressure, and that's why high pressure is required in order to perform this reaction. So this is the important facts related to the Haber process. Here catalyst is also used, iron catalyst, and in order to enhance the efficiency of the catalyst, we also use some promoter, and that promoter enhance the efficiency of the catalyst. Recovery of ammonia, once ammonia form, that is liquefied, and and nitrogen hydrogen, those are not easily liquefied, so the nitrogen hydrogen easily removed from the ammonia. If any unreacted nitrogen hydrogen present that is mixed with ammonia, then ammonia is liquefied, and the other gases like nitrogen hydrogen, they should be removed from the ammonia. So this is the process of recovery. Some physical properties of ammonia. Ammonia is colorless gas. Intensity is less than air. It is alkaline gas, and the pungent smell. It is highly soluble in water. It is highly soluble in water. And the boiling point, freezing point, no need to remember those temperatures. But only important fact is that 702 volume of ammonia is 1 volume of water. These are the physical properties of ammonia. Now the fountain experiment is exactly similar to what we have already discussed in case of HCl. Now the difference is that the upper round bottom flask will be filled with ammonia gas, and the lower part is filled with red litmus. In case of HCl experiment, we use HCl gas in the round bottom flask, and the lower part should contain the blue litmus paper. But here just reverse should be taken and filled with ammonia gas, and mouth of the rubber stopper and jet tube, exactly similar arrangement. So red litmus paper go through this jet tube and forms blue, converted into blue. This reaction proves that ammonia is highly soluble in water, and also the ammonia is basic in nature, because of the fact that this red litmus solution is converted into blue as they comes in contact with ammonia gas. This is fountain experiment. And now some of the important reactions like you have to read this reaction where the ammonia reacts with oxygen with the formation of nitrogen and water. Greenish yellow flame, ammonia burns in oxygen with the formation of nitrogen and water. Burning of ammonia in oxygen without using any catalyst. Here you see that if you do not use any catalyst, then ammonia reacts with oxygen with the formation of nitrogen and water. But if you use some catalyst, here you see that you use some catalyst, then it is converted into nitric oxide and water. So this is one of the important reaction where the how ammonia reacts with oxygen in presence and absence of catalyst. Here, in absence of catalyst, form nitrogen, and in presence of catalyst, it forms nitric oxide. So catalytic oxidation of ammonia. This is catalytic oxidation of ammonia. Now ammonia gas is basic in nature because ammonia takes H plus. Ammonia donates its lone pair to H plus, so it is considered as Lewis base. Already we have mentioned that the species having capability to donate lone pair of electrons should be considered as the base. So ammonia is Lewis base, and ammonia. What is liquor ammonia? Liquor ammonia is the aqueous solution of ammonia. Liquor ammonia, aqueous solution of ammonia. It's called liquor ammonia. Liquor ammonia fortis, which having specific gravity is 0.88. The process of dissolution of ammonia gas is similar like that of HCl, where the special funnel arrangement is used. Already we have mentioned in case of HCl. So ammonium salt, the preparation, if you want to prepare the ammonium salt, then ammonia reacts with HCl. Ammonia, when reacts with HCl, produces ammonium chloride. When reacts with ammonium nitrate, it forms ammonium nitrate. When it reacts with H2SO4, then it forms ammonium sulfate. These are the some ammonium salts may be prepared. It reacts with nitric acid, sulfuric acid. Ammonia undergo thermal decomposition. When ammonium salt, ammonium chloride, it is heated, then ammonia plus HCl form. This is the thermal decomposition of ammonium salt. Now the most important part of this chapter, reaction, that is this particular part where the ammonia reacts with different metal cations with the formation of different types of salts, different types of precipitate, different colors of precipitate. Those reactions are already we have discussed in analytical chemistry chapter, where the aluminium it forms gelatinous white precipitate. Aluminium gelatinous white precipitate. Calcium forms calcium hydroxide precipitate. Zinc also it forms gelatinous white precipitate. Lead forms chalky white precipitate. Copper forms blue precipitate, and iron dirty green precipitate. Ferrous and ferric reddish brown precipitate. Ammonia do not form any type of precipitate, but some of the precipitates are soluble like zinc, aluminium, iron, zinc, aluminium, lead, etc. They are soluble in excess 1, but the other is not soluble in excess 1. These are the reactions which is given the different types of colors in different metal ions. Already the last here you see that ferric hydroxide, and the ferric hydroxide, the precipitate of ferric hydroxide and the precipitate of ferrous sulfate, ferrous hydroxide, the dirty green and the reddish brown precipitate. And the zinc, when reacts, it forms the white precipitate, but excess dilute ammonium hydroxide, it is converted into colorless solution. So these are the important reactions related to the ammonia. But this reaction is most important where the copper sulfate, small amount of ammonium hydroxide gives blue precipitate, but the greater amount of ammonium hydroxide gives deep blue solution, cuproammonium sulfate, the deep blue solution, which we can perform in the laboratory. Now, the reducing property of ammonia, when ammonia gas reacts with lead oxide, it reacts with ammonia with the formation of plus lead plus nitrogen plus water. So this type of reactions can prove the reducing properties of ammonia gas. Here you see copper oxide also reacts similarly to form copper and nitrogen and water. So if in the exam asks that which reaction proves that the reducing property of ammonia gas, then you can use this type of copper oxide or lead oxide, this type of. Another important reaction, that is the reaction of ammonia with excess amount of ammonia gas. Ammonia is excess, where nitrogen and ammonium chloride is formed. But if chlorine is taken as excess, then NCl3 will be the major product. Okay? Ammonia, when excess amount of ammonia, then ammonium chloride is the product. But if the chlorine is excess, then you get NCl3. So two different reactions, so the excess ammonia or the excess chlorine. Excess ammonia means ammonium chloride and excess chlorine means NCl3. And the process of reaction of ammonium chloride, where the ammonia and the chlorine HCl reacts with the formation of ammonium chloride, identification of ammonia gas. And this is also identification test of ammonia gas, where the copper salts gives blue precipitate and the deep blue solution when the excess amount of this compound reacts. Nessler's reagent, another important reagent that can be used to identify the ammonia gas, because when Nessler's reagent reacts with ammonia, give the deep brown precipitate. So this is another reaction to identify the ammonia gas. And some of the uses of ammonia, like ammonia can be used as laboratory reagent or preparation of different types of ammonium salts, like ammonium sulfate, ammonium chloride, etc. Those ammonium salt can be used to prepare by the use of ammonia gas. So this is all about HCl and ammonia gas. I share those specific PDF within tomorrow. And consult your book. At almost I cover all the parts of these two chapters. Okay, thank you. Good night.